All right, dude, we are live. What's up, guys? This is Dem Keys, and today we are going to continue learning about ESP32 Rust things. More specifically, we're going to be focusing on trying to understand how PWM works on a lower level, and even more specifically, we are trying to understand how the clocks within the ESP32 work. We spent most of yesterday's stream doing pretty much that, and we actually made some decent progress because I've got a much better understanding of how these clocks are working, how these clocks relate to how the PWM system works, or rather, I should say, how the PWM hardware uses these clocks. Give me a second while I get some background sound going. Let me also open up my stream chat on my phone. And additionally, here's something exciting. Now, I'd always wondered, so okay, if you look at the breadboard on the in the top right of the screen in the webcam, it's got a different shape now. Previously, it had a sort of L shape kind of thing. And what I'd done there is I'd taken three breadboards and I'd slotted them together because these breadboards they have like notches on them, and they have I keep confusing between, like, hold on, I'm gonna Google this so I can use the right terminology, because each time I'm confused about what should I be calling this. So give me a second here. In breadboards, you have these things on the side that allow you to sort of um, sort of um, slot in other breadboards, um, making it kind of modular. What do you call those things? Um, on one side, it's um, sort of an empty region that needs to be filled in, and on the other side, it's things sticking out that do the filling. Okay, those quote-unquote things are generally referred to as interlocking tabs and notches. Okay, okay. So the notches, I'm assuming, are the things that the tabs go into. Or maybe it's vice versa. I'm not sure. Um, or more simply, dovetail connectors. Because they allow you to connect multiple boards together to create a larger prototyping surface, they are the key to the modular nature of modern breadboards. True, true. I actually discovered this just like, well, okay, I didn't just discover the modularity aspect of it, but there was one specific thing that I'd words. Hold on. There's one specific thing that I had always been curious about. It was the rails on each side of the breadboard. So if you look at, um, so if you look at this breadboard, sorry, I have to find a way to speak into my mic while also showing the breadboard. Oh, wait, give me a second. I think we are on a bit of a delay with the RTMP feed. So let me just fix that. Yeah, that's better. So if you look at the breadboard here, you'll notice that there's two rails on. Oh, sorry, there. So if you look at the breadboard, you'll notice that there's two rails on either side. These rails, I'd always notice that they're kind of loose, meaning they probably come out. So like you can probably disconnect them from this board. And if you look at the other side usually comes with this. What should I even call this? It's like a double-sided tape kind of thing. So with double-sided tape, you have the tape itself, and it's got paper on both the sides, or it's got like some sort of covering on both the sides, and you have to remove that cover to reveal the sticky surface so you can stick to whatever. You have to remove the cover on both sides. So here what they've done is they've removed the cover on one side and stuck it to the breadboard, and the other side is still covered, so you can remove it if you need to. If you need to stick it to something, you can then remove it and stick it, or just leave it connected, or leave it covering the surface. And usually I just leave it covering because I need to be able to move the breadboards around. I don't necessarily want to stick them anywhere. Sorry, sorry. I'm watching um Sea Dog's Cyclothon, and Jay Schlatt just appeared on stream with a cigar. Okay, so um today I decided to try cutting in the in where I thought there might be um a space between the, what do you call it? Hold on. Here. Yeah. Today I decided to try cutting with like a paper cutter to see if I could separate the pieces. And as it turns out, yes, I can. Um, so this is what I did. So as you can see, I've separated the power rails on both sides, and now I can connect this in whatever way I want. Um, assuming the tabs and notches match up. So what I did with this breadboard is I removed the two rails that were there, and I replaced it with just one rail. So that's one rail here. And doing that allowed me to place the ESP32 directly in the center of this, because of which now, good news, I'm able to use both sides of the ESP32. Um, Previously, I wasn't able to do that. Dude, you know what? I should get some sort of stick to be able to point at the breadboard, because I have to sort of reach into this area to be able to do anything, and I have to like move my mic for that. And right now I'm sitting in like a odd position because of that. I need to readjust my position. Let me slot this thing back in, and then I'll readjust my mic. Give me a second. So, as you can see, now the design is um, definitely much more different than it was the last time in the last stream. And I need to order a couple more of these exact same breadboards. In fact, I'm looking for modular breadboards. I want to explore what different types of modular breadboards there are, because the modularity it helps. It helps a lot. I can get creative in terms of designing things. Also, having, a tiny breadboard would be very useful for various other purposes. Um, yeah. So now I'm left with this one rail, which I'm not going to be using. I could slot it here or there, but I could also just not use it at all. This is great. This is great because yeah, I can make this modular. I can design it however I want. I just need to buy more breadboards. I think I want to place an order maybe in the next day or two. I have a small list that I've set up. The list contains, so what all do I have? So, oh, dude, another thing. Yesterday, I was doing research on a couple of things. I do have a robotics project planned, but I was curious. I was like, okay, deep learning can't be the only way that robotics can be achieved. Neural networks aren't the only way that robotics can be achieved. I'm sure uh, prior to this, people have used various techniques. And so I did some research and I wanted to get a list and perhaps a bit of a description of the different programming concepts that I should be looking into. I don't know if I should call them programming concepts or algorithms or programming paradigms, but the paradigm is more about um, it's more about the way that you design the system and not about the the techniques being used in the system. Um, I was trying to do research on specific programming concepts that I should be looking into. And one of them was finite state machines, where you have like a fixed state, and anytime an action happens, you change that state, and depending on what the state is, based on an update loop of some sort, you can keep checking the state and take actions based on that. That's great for simpler tasks, but apparently it doesn't scale very well. When your project becomes very complex, then that can also become incredibly complex to handle. And so the next step from that is apparently something called behavior trees. And That's something I'm also going to be looking into. This whole thing started this whole thing started with me trying to find a way to do speech synthesis, but not the audio version, the text version. Uh, I was trying to I was trying to think of ways that I could, let's say I wanted to create a robot that did very basic greetings, said very basic sentences, maybe not something as intelligent as an LLM, maybe not even something that can hold a full conversation, but just something that can give text in some way, shape, or form. What should I be using for that? One of the techniques that Gemini suggested was something called Markov chains. So that's something I'm going to be looking into. Apparently, that allows you to control behavior based on certain weights that get updated depending on certain conditions. And that's a very interesting approach to take because that allows you to create fairly complex behaviors depending on things that have happened, depending on events that have taken place. I haven't fully explored it yet. I'm still looking into Rust crates for it. More specifically, any crate that I look into for this purpose, it has to it has to be no STD compatible. So that's a very important thing. I believe so I did find a finite state machine crate for Rust, and I believe it does also support no STD. Um, it has no STD support. I don't know what the limitation is. I'm going to have to look into that, but it does have no STD support. There's a behavior tree crate that I found, which is like specifically meant for that purpose and specifically meant for embedded electronics and robotics. So that's exciting because that's literally what I'm using it for. I'm using it for embedded programming. Um, and so it's no STD compatible, like out of the box. What else was there? Oh, all of this, somehow, all of this, it got me curious about Raspberry Pi again. See, in the past, give me a second. Okay, so uh, I've paused the Matrix Rain for a little bit, but yeah, in the past, when I did shit, I lost my train of thought. What was I gonna say? In the past, when I Oh, in the past, when I tried to do my Raspberry Pi stuff, my first little hurdle was actually getting the card reader to work. And the card reader that I had was a fairly old one. I have no idea if the thing worked properly or not. I managed to get the thing to work, and I think I managed to also um, flash the image on there. I don't remember which OS's image it was, but I'm pretty sure I managed to get the thing on there. The next little hurdle for me was getting the Raspberry Pi to work because I had to connect the thing via HDMI to a monitor. And then I had to plug the thing in and, turn the Raspberry Pi on, but there was nothing. Like the thing was getting powered. There was a little light that came on, a little LED that came on, but other than that, there wasn't too much else happening. There was definitely nothing showing up on the monitor. Sorry, on the TV that I had connected it to. And so I sort of like gave up on it. I believe the reason why it might not have been working at the time, though I assumed that, it would still give me some sort of output on the monitor, even if it's not able to boot well enough. But like the I have a doubt that maybe it was the phone charger that I was trying to use to power it, because you get dedicated Raspberry Pi adapters which run at they handle the voltage that the Raspberry Pi requires, because apparently the Raspberry Pi requires slightly more than 5 volts. So maybe it's 5.1 volts, I think. They require slightly more voltage, and depending on what you're using them for, their current draw can also be a little on the heavier side, often heavier than what a phone charger can provide. Because the phone chargers give you like 1 to 2 amps. 2 amps is usually the max, and there are some that don't even go up to 2 amps. But apparently, the Raspberry Pi charger gives you around 3 amps, if not more. So I thought I could get away with trying to power it with a phone charger, but I was wrong. I never managed to boot up my Raspberry Pi properly. So there were a couple of things that kind of, created hurdles for me. So this time around, I want to, first things first, I want to order a Raspberry Pi adapter. Fortunately, they are cheap. I don't have to, go and buy the expensive one. I'm gonna get one off of AliExpress that has the best reviews. I'll make sure to read the reviews from other people. Same for the SD card reader as well. There are much better SD card readers now, much smaller. I found this one that is like it literally looks like a flash drive, and it has the slot for putting in um, a micro SD card and also one of those big SD card jackets. So I need to order one of those. I also want to order two, if possible, three modular breadboards, pretty much this exact size, the size that I'm using right now, because um, I want to be able to set the entire thing up in whatever way I want. I want to see like how different I can make this design, because there's a lot that I can do with this. Um, yeah, there's quite a bit that I can do with this. The way that this has been designed is interesting. Um, it allows for interesting designs. I also need to check if there are other, because like, okay, for now, I already have three of these specific types of modular breadboards. So I want to get new breadboards that are the exact same type as this, so that I know that I'll be able to take them apart and then, fit them into this setup. Otherwise, if I buy breadboards that are of a different type and they're different sizes, they have notches in different places, then it's just going to be a mess, because I'm not going to be able to customize this thing that I'm trying to customize. So yeah, I need to look into modular breadboards. Another thing I need to look into, speaking of breadboards, is the MB102, which is um, essentially a power rail for your breadboard. It's meant to be plugged into the breadboard, and you get, like, it's a chip. The chip has pins that you plug directly into the rails of your breadboard, and it has jumpers that allow you to switch between 5 volts and 3.3 volts. It also, because it goes on both sides, um, it allows you to choose between 5 volts and 3.3 volts on individual sides. So like one side could be 5 volts, the other side could be 3.3 volts. I found that interesting. Something I'm so glad that I found out about this before I accidentally melted something is that apparently the MB102 does have current limitations. If you're planning on driving, let's say, a DC motor module, you definitely don't want to run the power through this, because in this chip there are other components. One of them is a voltage regulator, and various other components as well. But the voltage regulator, at the very least, could possibly melt or burn or whatever if you pull too much current from it. At least that's what Gemini is saying. That being said, whatever it is that could break, I don't want to test whether it's going to break. Um, One amazing thing about this is that once I've done this, I will be able to power a breadboard without needing a microcontroller. So if I ever want to set up a very simple, LED circuit, I don't necessarily need um, like AA batteries, even though I do have like the battery pack and I have the AA batteries. In this case, I can just like plug the thing into either a power bank or what do you call it, into a power bank, or a phone charger or something like that. I should look into reverse polarity protection, like, because I feel like the the diode to protect from that might not be included. And yeah, I need to look into like the details surrounding that. Then another thing I need is assorted trim parts, because these uh, these trim parts, which I don't know if it's visible. Yeah, that's the trim part. This is basically I think it's called a trimmer part or a trimmed potentiometer or trimmer potentiometer. One of these two. It's basically a variable resistor. It's a potentiometer. Um, but like you can plug this into your breadboard or even into your circuit, and you can turn the dial. These aren't meant to be constantly change. They're meant to be more of like tuning, circuit tuning kind of things. So it's more like if you need to tune something on the circuit itself and like set and forget kind of thing, then you can use this. Whereas the bigger potentiometers, generally they're meant to be handled constantly. So like there'll be a hand constantly turning the knob. In this case, it's like every now and then you might want to tune something, but you won't. Uh, it's not one of those things that's meant to be necessarily, user facing. Though in my case, user facing doesn't really mean much because I'm the one developing the circuit. I'm the one building the circuit. But yeah, I need assorted trim ports because these are great to like plug into the breadboard, and it works out much better than the other potentiometers that I have. Um, I don't even need to worry about like soldering anything with this. I can just plug the thing in and then plug in some wires and we're good to go. The next thing and final thing that I need is force sensitive resistors. I found this concept very interesting because this basically gives me a way to um, set up a sort of touch sensitive thing. So you pretty much need to apply some sort of force along a surface with these resistors, and the resistance kind of changes depending on the force that you're applying. I am curious about how force is measured when because you have different types of surfaces. You have like a square, you have a circle, you have a strip. So with a strip, it's going to be a long strip that you can run your finger across. With a square, it's a 2D surface that you can like move your finger across, and the same with a circle as well. So I need to see how exactly they are measuring stuff there. And I just remembered I should also probably because the TFT displays that I have, some of them or all of them, I don't remember. They've come with capacitive touch displays, and that capacitive touch is what I'm interested in because this makes me wonder if I could get something similar um, to maybe track, like imagine a drawing tablet kind of situation. So I'm wondering if I could like create something like that. That would be very interesting to set up. Okay, so let me ask Gemini. Hey, so I've read about what are they called? Force resistive force. What is the S? FSR. Force sensitive. Okay, force sensitive resistors. Um, with I'm wondering how they work and how I would be able to use them. Like, would I be able to track uh, t- track 2D position within that surface if it's one of those square surfaces? Also, um, a while back, I had bought a couple of um, TFT displays, and some of them came with capacitive touch um, displays. I do ESP32 projects using no STD Rust. This has me wondering whether this has me wondering, no, and I know that the ESP32 also has touch capability. This has me wondering how the touch displays work and how would I know, and whether I could get something cheap that I could use to track 2D position, kind of like a drawing tablet. I don't think I should say track 2D position because that makes it seem like there's a tracker that's moving in 2D space. But really, what I'm trying to track is the position where we are currently pressing on. Okay, that sounds like a fun rabbit hole to dive into. Combining no STD Rust, the ESP32 and DIY input devices is a great way to learn about signal processing and embedded drivers. Here's a breakdown of how these technologies work and how you can use them for your 2D tracking project. Force sensitive resistors. FSRs. Standard FSRs, like little round ones, are 1D sensors. They only tell you how hard you're pressing, not where. Okay, okay. How they work. Inside an FSR is a sandwich of two membranes. One has conductive traces like fingers, and the other is coated in a resistive ink. Resting, the ink doesn't touch the traces much, so resistance is very high. Pressed, pressure forces more ink into contact with the traces. This creates more paths for electrons to flow, dropping the resistance significantly down to 1 kilo ohms or less. Okay. Can you track 2D position? With a single FSR, no, it's just a variable resistor. With an FSR matrix, yes. Professional pressure maps use a grid of rows and columns. By scanning which row slash column intersection is has low resist. Okay, you know what? I get that. I get that. With when you have a grid, when you have a matrix, so you have multiple FSRs, then depending on which one has the most or least resistance. I think least resistance, yeah, because when you press it, uh, then there's more surface for the electrons to flow. So depending on which one has the least resistance, you can then detect that, hey, there's so and so, there's pressure at so and so position. Okay, shunt mode linear FSRs. These are long FSR strips that act like potentiometers, letting you track 1D position along the strip. This lets you track 1D position along the strip. I think those strips that I was looking at, they might have been shunt mode linear FSRs. I'm not sure. But okay. Project tip, if you want 2D position with FSRs, you need a matrix array. They're great for drawing because they provide pressure sensitivity natively, which capacitive screens, which, holy shit, what just happened? Which capacitive screens struggle with. Okay. Capacitive touch, ESP32 versus dedicated displays. There's a big difference between the touch pins in the ESP32 and the capacitive touch, quote unquote, on a TFT display. ESP32 built-in touch pins. These use surface capacitance. The ESP32 charges a GPIO pin and measures how long it takes to discharge. When your finger, which acts as a capacitor, touches the wire connected to that pin, the capacitance increases and the timing changes. This is best for simple buttons or sliders. Limitation, it's hard to make a high resolution 2D grid with just these pins because you'd need a massive amount of wiring and GPIOs. Okay. Capacitive displays. These use projected capacitive touch, PCAP. there's a transparent grid, ITO, on the glass, a dedicated touch controller chip, like so-and-so or so-and-so, sits on the display ribbon cable and handles the complex math of scanning the grid and interpolating your finger's position. Okay, how to use it with Rust. You don't read raw analog values. Instead, you talk to the controller over I2C. All right. Building a cheap drawing tablet, the Rust way. Um, okay, okay. You know what? For now, I'm gonna let this one. I'm gonna put this one to the side for the time being, while we continue doing research the on the math behind this clock stuff, because I've been making progress in terms of understanding what's going on here, and I'm almost I would say I'm almost ready to get into the calculations. So we have a couple of things here. Okay, for the sake of for the sake of you guys being able to read the, I hope it opens the right project. Okay, yeah. For the sake of you guys being able to read the formulas, I'm going to type them out here. Give me a second. I need to go to the Scratch thing. Okay, so we have a couple of formulas here. Okay, we have f underscore, wait, wrong. We need to enter insert mode. Okay, f underscore pwm equals um, f underscore led c underscore clock divided by clock underscore divider multiplied by 2 to the power of res underscore bits. So this is our FPWM formula. I'm assuming this means the PWM frequency. Oh yeah, it says here the frequency of the PWM signal, FPWM, can be calculated by so and so. Now we know what LEDC CLK is. So we're gonna just type that out here. This is equal to 80 million. Okay, 80 million hertz, or 80 megahertz. Okay, we don't know what the clock divider is yet. We get to set that. Um, we also don't know what res bits is, and that's an interesting thing because like we get into that later on. Um, why is this taking so long to do its thing? Was there like an update in? I'm wondering if I should have used like the locked versions of these. I don't even know if that's an option when you're adding dependencies to your project. I don't even know if it's an option to add locked versions. I don't think they should update automatically. I don't know why it's having to do this compilation thing. Um, usually that would be a little faster, but yeah, whatever. Okay, so that's our formula for PWM signal frequency. Okay, great, awesome. Then the next thing is the PWM duty resolution formula. PWM duty resolution. This is the formula derived from the previous formula to calculate the desired duty resolution. Okay, PWM duty resolution formula. Formula. Okay. So res underscore bits equals log2. So this is a base 2 logarithm of this, whatever the result of this calculation is. So FLEDC underscore CLK divided by FPWM multiplied by clock underscore divider. So that's our so this formula gives the duty resolution in bits, which represents the number of discrete levels available for the duty cycle of the PWM signal. Okay, all right. Okay, so this is basically the number of ticks are this is the number of ticks that are one period of the frequency is gonna consist of. All right, great. Then the next is calculating the highest resolution. Calculating the highest resolution. Okay, we're gonna write down this formula as well. Uh, highest underscore res equals log2 um, f LED clock divided by f underscore PW. Well, this is, yeah, this is basically just the frequency. So it's the clock frequency, the source clock frequency divided by the PWM frequency, the desired PWM frequency. That gives us the, well, the log 2 of that gives us the highest resolution. So this tells us what how many bits we want to use. So hold on, let me save this and try doing this here. I was actually doing the calculation here earlier. So for example, if our clock speed is our source clock speed is 80 million, dude, I'm glad that I found out about this thing. The crazy thing is I've done Python for a good decade. I had done Python for a good decade before it occurred to me to try something like this when working with big numbers. Fortunately, I wasn't in too many situations where I had to work with big numbers, but there were some situations where I had to work with big numbers. Um, the main issue for me tends to be this. Uh, trying to count something like this, it can become a bit of a nightmare for me. I don't know if it's just like a regular thing, if other people also had this issue, but like I definitely had this issue. There are what, 8 zeros here? Sorry, 7 zeros. This is an 8-digit number. There are 7 zeros here. Um, but like if I want to count these zeros, I can't just count it visually. I'm gonna have to do this. 1, 2, 3, 4, 5, 6, 7. Like there has to be something showing me, hey, okay, this is where you are. Because the numbers, they kind of start to, the numbers kind of start to like mix up when they're all laid out together. I don't think that's just a me thing. I'm pretty sure a lot of other people as well, when they look at, a list of the same number, or like let's say, I don't know, a number with 10 fives in it, and they start counting, at some point they might lose track of their count. It can happen because all the numbers look the same. Anyways, so here, oh yeah, we also have to do this thing, right? So let's, do we have log2? Do we have math? We have math. Math dot log2. Yes, we have log2 as well. So here we want to do 80 million divided by PWM. So if we want our PWM to be, let's say, 10K, um, our highest resolution is going to be either 12-bit or 13 bits. It should be 13 bits when I'm looking at this kind of a number, because like it's hard to say which side I should go with when I see a decimal and we are counting bits. We can't really do decimals, when counting the number of bits. So if we have to pick one or the other, I prefer to go for the higher one. just because I know that everything is going to fit within that higher number of bits. But then there have been situations where or like within, I think it was either in this documentation or in the explanation that Gemini was giving me, that it mentioned when there was, I forgot the exact number. I think it was 12.2 or 12.3 or something. And Gemini was like, yeah, this can be called 12 bits. I was like, okay, what about that remaining zero point 0.2 or zero point 0.3? Because that tells me that there might be a little more there. So if we go to the absolute maximum value, we might hit the limit much quicker. That being said, we are trying to calculate the highest resolution here, right? We are trying to calculate the highest resolution, that a PWM frequency of 10 kilohertz is gonna reach. Sorry, hold on. This is the highest resolution for one period. Yeah, I just realized that this is, or I just remembered that. This is the highest resolution. So we are talking about 12 bits. Um, Hold on, what is it? Zero? Uh, does that work? That works. Okay. Okay. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 4096. So we can fit 4096. Really? Is that true? No, wait. No, something seems off here. Oh, no, no, no. You know what? No, no, no. It's not off because 8 bits. Yeah, yeah. No, it's not off. Because I was thinking about like higher numbers, but the higher numbers usually come around 16 bits and 32 bits and stuff like that. So 8 bits is 256 values, and then 9 bits is 512, 10 bits is 1024, um, 11 bits is 2048, and 12 bits should then be 4096. Okay. Why was I doing this? Oh, yeah, yeah. So if we say 12 bits, right? Um, if we are giving this 12 bits, if we are setting, so we set the frequency, right? The frequency gets set, and then we set up the resolution. Okay, so I was having this conversation with Gemini yesterday. I don't remember if this was off stream or on stream. Um, but like, hold on. PWM hardware explained, because I had a sort of like light bulb moment where it was like, okay, hold on. I'm trying to understand how um how the frequency and resolution are connected, yet we are able to specify both the frequency and the resolution. And it turns out that no, we are not specifying the resolution. But okay, we so we specify the resolution to specify what the maximum value can be of the number of ticks within one period in within the frequency. We are specifying the resolution for that, and when we specify the frequency, we are specifying how many periods are present. Though I don't understand how frequency and resolution are related. Then see, now I'm getting that confusion again. Hold on. Hold on. I had this light bulb moment yesterday, and I need to bring that back. I was also doing research on the various other clocks that the ESP32 has. Oh, yeah, it was in this conversation. I said, okay, so a couple of things. So this has been super helpful. This made me realize that I was kind of confusing the ticks of the source clock with the ticks happening within each page. Okay, yeah, that was a different thing. That was more about comparing the ticks happening within the source clock with the ticks happening within a specific period. And um, I think what I was confusing there, or what I was not able to understand there, was why we were doing the whole division thing, or how we were doing the division thing. Okay, then the second part of your answer made me realize that setting the frequency and resolution are connected in that when we set a frequency, we are then able to determine what the resolution. Oh, they're connected in that way. No, 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 hold on. This is coming back to me. Hold on. I'm glad I didn't close this conversation. I'm glad I kept it open. We are then able to determine what the resolution will be. But when we set the resolution, we are setting the max value that the frequency could be. See, that last part confused me. When we set the resolution, I don't think I meant to say frequency there. I don't think I meant to say frequency at the end there. I think I meant to say, but when we set the resolution, we are setting the max value. Why did I say frequency? I think I meant to say the maximum number of ticks that each period within the frequency can be. Why did I just write frequency there? Okay, well, Gemini responded saying, you nailed it. You have effectively debugged your mental model of how silicone handles time. To wrap this up into a clean, professional engineering perspective, let's look at the 2 points one last time. The tick hierarchy, you're exactly right. There are two different layers of ticking happening. Layer one is the heartbeat. This is the 80 megahertz source clock. This is the absolute physical limit of the chip. It is the global tick, quote unquote. And then layer two, that's the derived tick. This is the PWM counter. This is the local tick that you actually interact with in your Rust code. If you use a prescaler of 8, your local tick happens once for every 8 global ticks. Your PWM peripheral is effectively breathing slower than the rest of the chip. Then, the frequency slash resolution equation. Your realization that setting one limits the other is the fundamental trade-off in PWM design. In no STD Rust, you will often see this represented by a single budget equation. Since the ESP32 has a fixed 80 megahertz clock, the relationship is 80 million, it says 80 million greater than or equal to frequency multiplied by the resolution bits. I didn't understand that statement that was made there, but okay. Um, Hold on. What was I confused about? I'm kind of lost on that. So we set. Hold on. I'm gonna open up a new conversation with Gemini. I'm learning about the ESP32 and also learning about NoSGD Rust coding in ESP32. NoSGD Rust coding for ESP32. I'm currently learning about PWM and the 80 megahertz global tick, help me understand how frequency and resolution, how the frequency and resolution that we set independently um, are somehow related to each other. Man, I had this down yesterday, and then today I'm lost again. I feel like I need to do this practically in order to understand the calculation. Okay, it's great that you're diving into NoSTD Rust on the ESP32. It's a rewarding, if slightly mind-bending, way to get close to the metal. Sorry, zoned out. The relationship between frequency resolution and that 80 megahertz clock is essentially a balancing act of slicing time. Here's how they are tethered together. Okay, think of the 80 megahertz clock as a high-speed metronome. Okay, yeah, I've gotten that part. Every hardware peripheral, including the LEDC PWM controller, uses these ticks as the fundamental heartbeat. Okay. The hardware takes the 80 megahertz clock and passes it through a divider or prescaler to slow it down to a manageable pace. Hold on. There's a prescaler already. There's a divider already set up. I think this is what gets covered in the next section, isn't it? I think so. So if there's already a prescaler, all we are trying to do here is understand um, why things are being done. Yeah, it says here the prescaler is used to reduce the base clock frequency before it's applied to the PWM signal. The MC PWM is driven by a clock with a frequency of 160 megahertz. That's new, meaning it ticks 160 million times per second. This clock serves as the base frequency for the MC-PWM module. However, the prescaler modifies the base frequency by dividing it, effectively reducing the clock frequency that the PWM signal uses. Okay, so there wasn't a prescaler mentioned in the previous thing. Holy shit, dude. Here's the yawning again. Shit, I was supposed to Google that, but I kind of got busy doing other stuff and just forgot. Anyways, okay. Um, the relationship, the bucket analogy. Okay, frequency, how many no, no. Hey, can we do this without analogies? Fair enough. Let's look at the raw hardware mechanics. Um, okay, the hardware counter mechanism. Um, the timer is so and so. Okay, the frequency calculation. So the frequency calculation is the frequency is determined by how long it takes for the counter to finish a full cycle. If your resolution is 10-bit, the counter must count from 0 to 1023. If we assume a clock divider of 1, so no slowdown, the time it takes to complete one cycle would be the resolution divided by FCLK, which I'm assuming is 80 megahertz. Since f equals 1 divided by t, the frequency is FCLK divided by um, the resolution. Okay, yeah, that's not here. That was somewhere here. Wait, let's go along with it. The inverse dependency. Because the numerator FCLK equals 80 megahertz is a constant, the frequency and resolution are inversely proportional. Increasing resolution, if you increase the resolution from 8-bit to 16-bit, the counter has to count to a much higher number. Okay, this takes more time, which inherently decreases the frequency. Okay, increasing the frequency, if you need a faster frequency, the counter must reset sooner. The only way to reset sooner without changing the clock speed is to reduce the number of steps it counts, which decreases the resolution. True, true. Wait, so if we try to achieve. Oh, we cannot. So it is, I need to write this down. It is limited because of the fixed, it is limited because of the fixed tick speed of the global clock. Okay, okay. Wait, am I understanding this correctly? Um, the reason why the frequency and resolution are sort of dependent on each other is that um, one tick, one global tick, uh, wait, one global tick given um, a clock frequency of 80 megahertz would be 12.5 nanoseconds. So the issue here is that if we um, reduce the frequency or increase, if we increase the frequency, the tick speed doesn't magically shrink down. It remains the same. Um, Thus, we must. So we are talking about increasing the frequency, right? Yeah. Thus, um, to make sure that the ticks remain the same, we must change the resolution instead. I'm hoping I got this right. Okay, precisely. You have nailed the physical constraint. The 12.5 nanosecond duration of a single 80 megahertz tick is the atomic unit of time for the ESP32's hardware. I forgot about this, that the ESP32 does not have a concept of time. Um, it has a concept of ticks, and the ticks just so happen to be within 80 megahertz clock. The ticks just so happen to be 12.5 nanoseconds long. How did we come to 12.5 nanoseconds? Oh, was it 1 divided by 80 million? No, I don't think it was 1 divided by. Yeah, I think it might have been, right? Let's try that. Yeah, 12.5 nanoseconds. That's how we got it because 80 million megahertz. Oh, sorry. 80 million megahertz. 80 million megahertz means 80 million cycles per second. Sorry, did I say 80 million megahertz? No, 80 megahertz is 80 million hertz, which means 80 million cycles per second. So if we want to find out how long one or what duration of that second is occupied by one cycle, we do 1 divided by 80 million. Okay, okay. Shit, I need to write this down somewhere because I'm going to forget this. I need to write this down somewhere. Let's go back to this thing. Oh, wait. What am I in right now? How did we... Oh, wrong thing. Here. Okay. I was confused for a second. Um, Ask Gemini. No, write down later. ESP32. APB underscore CLK. Frequency is 80 megahertz. This means 80 mil cycles per second. One cycle is 12.5 nanoseconds long. This is what causes an inverse relationship between the PWM frequency and the PWM resolution, because the ESP32 doesn't understand time, rather it understands ticks, and one tick is 12.5 nanoseconds long. If we, for example, increase the frequency, oh, I should also mention somewhere here. Hold on, where? Okay. The ESP32 doesn't count time, it counts ticks. Actually, I should write this down somewhere. Um, 80 million cycles per second. One cycle is 12.5 nanoseconds long. Here. Okay, yeah, now I get it. Nanoseconds long. The ESP32 doesn't count seconds. It counts ticks. One tick equals one cycle, equals 12.5 nanoseconds. There. Yeah, I don't need to... Okay, what was this? Because the ESP32 doesn't understand time, rather it understands ticks, and one tick is so-and-so. Okay, all that is done. Because the ESP32 counts in ticks, if you, for example, increase the frequency, the tick length remains the same, and so you must change the resolution. Um, so what were we saying? Increasing the frequency. You must reduce um, the resolution to accommodate for that. Thus, higher frequency equals lower resolution, and vice versa. I need to test that. I need to test this last part out. I'm not entirely sure what I'm saying here is accurate, but just that last sentence. The other stuff, I get it. I need to write this down somewhere, dude. I feel like, yeah, I need to write this down somewhere. I need to create like a diagram or something so I'm going to remember this shit because I'm going to forget this later. This relationship, I need to find a way to remember this. Do I need to remember this? I don't know. Hold on. I think I need to remember for the sake of understanding why it's necessary, but then yeah, I need to find a way to remember this, dude, because I'm going to have this confusion again, and then I'm going to have to do a bunch of research again, and then eventually I'm going to come back to the same result again, but after wasting a good couple of hours. So I need to write this down somewhere that I'm actually going to remember it. I do have my journal, which is reminding me that I was supposed to create that project. My what do you call it? My website project, my knowledge base project. I was supposed to create that, and I was also supposed to create my website, which was going to host the knowledge base, and I haven't done any of that. That's crazy, dude. Actually, uh, things to do. Perhaps I should add the website. Zola website and um, knowledge base. Well, Zola website, um, knowledge base. Actually, yeah, I mean, I'm gonna have the knowledge base as a separate thing on GitHub, but um, yeah, let's say yeah, knowledge base, Rust. Okay. Give me a second here. All right. So this is saved. Now we can get back here. Okay. Um, now, wait, give me a second. Let me hydrate and then I'll continue reading. Okay. Um, right. Okay, precisely. You have nailed the physical constraint. The 12.5 nanosecond duration of a single clock, of a single 80 megahertz tick, is the atomic unit of time for the ESP32's hardware. It is a physical reality of the crystal oscillator and the APB bus. It cannot be compressed. Since the hardware cannot make a tick happen faster than 12.5 nanoseconds, the only way to change the duration of a PWM cycle, dude, I'm sitting here and wondering if I was trying to learn this shit by myself and there was no LLM, like LLMs weren't a thing, imagine the nightmare it would have been for me trying to understand this by going through, I don't know, 5, 10, probably not going to be 10, but like a good 5, 6, 7 different forums and looking at a good maybe 10 to 20, that might actually be 10 to 20 different threads, reading people's, different explanations and stuff and trying to piece the information together to see how it applies to my situation. And oh my God, dude, that would have been awful. In terms of doing research, LLMs have been just an amazing thing for me. Uh, I should mention they're amazing if you are using them to learn stuff that they have actually been trained on. Um, because if it's something that they haven't been trained on, they're probably going to make shit up. Fortunately, the stuff that I'm doing research on, like hundreds of thousands, if not millions of people have already done this. So like there's an insane amount of information available on this. And well, microcontrollers like the ESP32 are open source. Majority of it is open source. Certain parts cannot be open source because they didn't develop the tech. Um, I believe, yeah, I believe it's because they didn't develop the tech. I don't think it is their own tech. I could be wrong, but I remember doing research on this because I was confused about this thing, right? There were certain things that hadn't been fully implemented on the Rust side, or they had like partial support, partial implementation, or something like that. Specifically, this had to do with RF related things. Anything that involved RF tech. On the ESP32, the RF tech would be Wi-Fi and Bluetooth, and that confused me because I was like, "Hold on, why is that such an issue? Like, isn't the ESP32 completely open source?" Like I was assuming that that would mean the firmware is completely open source, and so is the hardware, right? The entire hardware design should be open source, or maybe people might be able to like take it apart and reverse engineer it or whatever. Um, but like the reverse engineering part is the harder route. That's a much harder route than actually just getting the source handed to you. So I was wondering that, and so I asked Gemini. I was like, "What's going on here? Isn't this supposed to be completely open source?" And then Gemini said that yes, this is for the most part open source, but certain things cannot be open source, not because they don't want to, but because legally they cannot open source it because it's not their tech. And I believe it was Gemini that had told me that their RF tech, it's not made by them. They have licensed it from some other company that doesn't allow them to open source it. And so the best that they're able to do is give you a binary blob that you interface with in order to get this thing to work. And so the community has been, over the years, they've been trying to reverse engineer the behavior through whatever tools they have available to them. And they've made decent progress. It's not like full support. There is still like a bunch of work to be done, but there's also a lot of progress that has happened so far. I believe the specific ESP32 that I have, it does have full support. Though, okay, you have a couple of different things. You have Wi-Fi, you have Bluetooth. I believe ESP now is also one of the things. I don't remember. I'm gonna have to check. Also, yeah, I was about to say don't take my word for it with the closed source thing. Um, but I don't think Gemini was wrong about that. Yeah, I don't think Gemini was wrong about that. I'm not sure though. But yeah, I'm assuming if they could open source the entire thing, for the most part, like the majority of the thing is open source. It's they're open sourcing whatever they can, but this specific thing, I'm guessing they cannot open source it. And I'm hoping Gemini is right about the fact that it has been licensed from a different company, um, which doesn't allow to open source it. Actually, I think I could load up that conversation again. Because on the machine where I'm doing Gemini stuff right now, it should have the conversation saved. ESP32 open source. Building robots, Rust FPGA, um, Wi-Fi security. Okay, ESP32 not open source. Give me a second. I'm still just looking through this. Okay, okay. ESP32. Give me a second. Hey, so a while back we had a convo about ESP32 not being fully open source, and you had explained to me that some tech of it is not open source, and it's not because they don't want to, but rather because they have licensed it from another company. Uh, can we explore that whole thing again? I've forgotten what you told me. Okay. Now, while this response comes, okay, it's a fascinating bit of industry behind the scenes that explains why even the most hobbyist friendly chips often have a black box inside them. The ESP32 is a bit of a hybrid. While Espressif, the manufacturer, is famously supportive of open source, their entire ESP IDF development framework is on GitHub. Um, they hit a legal brick wall when it comes to certain parts of the hardware and the radio. Here's a breakdown of why those specific parts remain closed. The brain, the process. Wait, I didn't know the processor is also part of. Yeah, I didn't think about that, dude. Yeah, dude, the processor is also part of this setup. For some reason, I was assuming that's part of the open source design as well. Okay, the ESP32 doesn't use an open architecture like RISC-V, though their newer chips and the ESP32C3 finally do. The newer chips like the ESP32C3 finally do. Okay, so now that I know that RISC-V is open source versus Extensa, um, I'm kind of more interested in RISC-V. Not that it makes a massive difference to me. It's mainly just the open source thing. It does not make a difference to me, at least not so far. Considering the very simple stuff that I'm doing with ESP32s, the kind of processor doesn't make a difference to me. Though I will mention this, probe RS is also another factor why the processor would make a difference to me, because with Extensa, I can't do probe RS stuff. With RISC-V, I can. Um, with Extensa, I also need ESP up, so I need a separate Rust toolchain. With with RISC-V, apparently it's part of the Rust mainline. So all I would need is, I'm assuming all I would need to do is add the target, and the rest will be handled. So I mean, I do have motivations to start using newer ESP32s instead. And I'm yet to solder the header pins onto my ESP32 C3 Super Minis. To be honest, I'm not that comfortable with doing it on the Super Minis, because dude, you look at those things, they've got components on them that are the size of a grain of a grain of salt, and I'm not even exaggerating about that. They've got components on them that are so small that I can't even see them. So like if I accidentally move something, I won't even know how to fix it. That's why I need to be like super careful with doing this. I'm still, trying to get better at soldering. I'm not all the way there, but I'm trying to get better at it. Fortunately, these header pins are mainly on the edges of the board, and I don't have to go somewhere in between the board. I don't have to go somewhere in the middle of the board. So I'm hoping, I don't create too big of a mess or any mess at all. Okay, anyways, so the ESP32 doesn't use an open architecture like RISC-V, though their newer chips like the ESP32C3 finally do. Instead, the classic ESP32 uses the Extensa LX6 microprocessor. The licensing issue. The CPU architecture is owned by Cadence Design Systems. The constraint, while Espressif buys the rights to use the blueprint, that's the IP core, in their chip, the contract strictly forbids them from publishing the underlying RTL, that's the quote unquote source code for the hardware logic. If they shared it, they would be giving away Cadence's multi-million-dollar intellectual property for free. All right, that's fair. And I believe it's a similar thing with the radio as well. I didn't in the last time I had this conversation with Gemini, I'm wondering now how I got to that conversation. I'm wondering if I got to that conversation through the radio related stuff, because I'm thinking that maybe at that time I'd found out that the radio related stuff is not fully open source, and that is why I had asked that question to Gemini, and that's when Gemini mentioned that, okay, for radio specifically, this is the case. Okay, speaking of radio, let's move on to the next section, the radio. Wi-Fi and Bluetooth stacks. This is where you usually encounter the infamous binary blobs. If you look through the ESP IDF folders, you'll find files that end in .a or .lib. Does that say .a or .o? I think it says .a. .a or .lib. These are precompiled chunks of code that you can use, but you can't read the source. Third-party IP. Parts of the Wi-Fi and Bluetooth hardware logic are often licensed from specialized RF companies like Seva or Riviera Waves. Okay. Just like the CPU, Espressif is legally bound to keep the secret sauce, well, secret. Regulatory compliance. This is also a practical reason. To get FCC and CE certification, a chip has to prove it won't misbehave and broadcast on forbidden frequencies. Oh, okay. By keeping the low-level radio timing and power control in a closed blob, manufacturers make it much harder for a user to accidentally or intentionally turn their ESP32 into an illegal radio jammer. Dude, this is crazy. And this is also why I'm so interested in RF tech. Because, dude, see, something like this, they cannot stop it from happening. They cannot stop it from, because of how RF works. There are certain things that they just cannot stop from happening. And that's why they have to make it illegal or incredibly hard for somebody to do to play around with it. They barely have proper safeguards for it in place. So it's just illegal to do it. That's crazy, dude. No, it's not crazy that it's illegal, but like it's crazy how wild this tech is. And this is why I'm like so interested in RF, dude. Like that's why it's so interesting to me, the concept of RF. But I can't go deeper into RF until I've gotten a certain amount of analog electronics related knowledge, so much that I'm comfortable enough with going into RF tech later on, because doing RF tech properly is incredibly complicated. RF is not a simple thing to get into. It is incredibly complex. Even the simplest things, the smallest of things that we are able to do with these, the NRF module and other like simpler 443 or 433, what is it, megahertz or hertz or what? It's one of these frequencies that a bunch of like the toys and cheap appliances and stuff use. Even something like that would be complex to create and do properly. So like even something like that would be too complex to implement. But then imagine the more actual complex RF stuff. It is crazy how complicated RF is, but I want to get into it. Okay, the shift to RISC-V. You might have noticed that the newer chips like the ESP32C3 and ESP32H2 are marketed as being more open. They switched from the licensed extensor cores to RISC-V, which is an open standard instruction set. Because they don't have to pay a license fee to Cadence for RISC-V, they have much more freedom over the tool chains and documentation of the CPU itself. All right, okay. We are going to get back to what we were doing here before I get too distracted and branch out way too much. Okay, so back to the ticks. Since the hardware cannot make a tick happen faster than 12.5 nanoseconds, actually, okay, I'm going to branch out again real quick just to ask a question relating to this tick. What was the question relating to the tick? I think my question was going to be, is it always 80? I forgot what my question was going to be. I'm going to keep this tab open so I can remember, or well, so I can type in the question faster the next time I remember it. What was my question going to be? So I've been having another conversation with Gemini elsewhere, or I think it's the same conversation. Yeah, I think I'd asked the question here saying, is this 80 megahertz fixed clock speed the only one? Or fixed clock? Is this 80 megahertz fixed speed clock the only one? And Gemini said no, but in the main character, but it is the main character for the peripherals you are currently studying. The ESP32 actually has a complex clock tree, while the APB clock, APB being Advanced Peripheral Bus clock, um, which usually runs at 80 megahertz, is the standard source for PWM, LEDC. There are several other gears turning inside the chip at different speeds. And then Gemini gave me a list of the other clocks. There's actually some of them are also mentioned here, I believe. At the time when I read all this, it did not make sense to me. Now that I know about this whole, separate clock thing, now I understand it. Yeah, yeah. Now that I know about the separate clock thing, I understand it. I also don't fault the creator of this tutorial for not going into that amount of detail, because the crazy amount of detail that I had to go into here to understand this whole clock speed thing, it would have made this tutorial or this section incredibly long. Whereas if you just stick to your higher level understanding of things, that hey, this is how things work, this is how you have to set stuff up, if you just stick to that, it'll be more than enough. For me, it's my curiosity. I need to, you know, understand it. So I took what's now been, I don't know, 3 or 4 days to understand this thing. Okay, so there's the CPU clock, there's the APB clock, there's a ref tick, there's a slow clock, and I think there was something else as well. Another question I'd asked is, can the 80 megahertz fixed speed change? Gemini responded by saying, while 80 megahertz is the default, it isn't strictly fixed in the sense that it can never be anything else. However, in no, I just remembered what my other question was going to be. Hey, so I'm learning about ESP32, um, no STD, Rust, and the ESP32 itself. I'm currently learning about PWM, and more specifically, oh shit, I'm losing the thing. I started giving this story and I'm losing the question. Hold on, hold on. Let me finish the story. And more specifically, what was the question going to be, dude? Okay, I was looking at this. Oh, it was the why. Okay, okay. Um, right. So, and more specifically, the APB clock and how the ESP32 handles time. Basically, it handles it in terms of ticks. I've learned that the APB clock runs at 80 megahertz, um, and that puts one tick at 12.5 nanoseconds in length. What I'm wondering is why. What I'm wondering is what controls this 12.5 nanoseconds length. What is deciding that this is going to be 12.5, that, wait, that one tick is going to be 12.5 nanoseconds long? Um, I'm assuming it's the frequency that is deciding that. But then my question is, what is controlling or deciding this frequency? There, that was my question. While Gemini answers that, I'm going to move on to the next thing, or the previous thing, which is here. Oh, okay. So Gemini was telling me about the speed of because like, okay, in order to generate these ticks, the ESP32 uses a crystal oscillator, and with a bunch of other circuitry in there as well to clean up the signal and give you like a standard signal. Um, you eventually end up with, thanks to this crystal oscillator, you end up with a fixed 80 megahertz signal. What was my question going to be? I forgot what I forgot where I was going with that. Yeah, okay, anyways, I was asking Gemini what the I was asking Gemini if there is a way to change that speed, or if it is like, fixed in the hardware. Okay, so Gemini said most ESP32 dev kits use a 40 megahertz external crystal. The internal hardware, the PLL, multiplies this by 2 to get your 80 megahertz APB clock. Then power management. If you tell the ESP32 to go into power saving mode, it might downclock the APB clock. Warning, if you do this, your PWM frequency will suddenly... You know what? When I was reading this and something else in another conversation yesterday, I came to a realization that with embedded hardware, something that I had not taken into account up until now is that you can have different sections of the hardware on and off, as in powered on and powered off, or powered down, or sleeping, or whatever. It's not like the entire thing has to be on and the entire thing has to be off. So, for example, one good example here is what Gemini was saying of, like, okay, there might be certain situations where your CPU is asleep, but then the PWM is still able to read the tick from elsewhere, read the tick from like a different clock, because maybe when the CPU is asleep, then the APV clock might be slow or might be off or whatever. I don't remember what the exact example was, but Gemini did mention that there's another clock that you can reference then when it's off. And then I was like, I did not think about this at all. That the CPU is not, because this is what happens when you're coming from like a desktop programming uh, environment, right? A lot of the stuff that you're doing, keep the GPU aside for for the sake of keeping things simple. um, a lot of the stuff that you're doing revolves around the CPU. You need the CPU to be on, right? But with the ESP32, apparently you can program various sections of the hardware to do stuff, and then the CPU can just go off, and those other sections can keep working. So this way you can conserve power and have the device run for much longer in extremely low power mode. Like, that's insane, dude. That's insane to think about. That's also going to be something incredibly important to keep in mind when I'm doing something that's really resource intensive, like robotics. That's going to be super necessary to to take into account when I start doing robotics stuff. You know what? Another thing I was looking into through Gemini yesterday was, so like, I'm planning on working on this robotics project, right? A simple robot pet type of project. And what I was thinking about was, how would I go about, like, let's say the device has been built, right? How am I, because keep in mind, this device has to, this device has, or this entire like circuit, this entire robot, it consists of a bunch of different parts. You have the ESP32, whichever one I decide to use. You have the ESP32, so you have the microcontroller. You also have two DC motors, because I'm planning on letting it use. Um, I'm planning on letting it use wheels to move around. So there's going to be two DC motors, and because they're DC motors, there's going to be a DC motor driver. Um, yeah, there's going to be a DC motor driver module, and that driver module needs electricity coming into it, or it needs, well, yeah, it needs current coming into it, which I cannot bring in from the ESP32. It needs to come from an external source, right? And then there's also going to be two servo motors, and those two servo motors are going to be controlled by a servo motor driver module, and even that module requires external current. It shouldn't be coming from the uh, from the microcontroller board directly. And there's going to be, I think, one or two other things. There might be a TFT display And but the TFT display doesn't necessarily need external power, at least from what I know. I'm not sure. But there's going to be these multiple parts, right? If I've programmed the microcontroller, if I've just flashed the binary onto the microcontroller and then soldered the entire circuit together, connected all the components, and then I connect that thing into like I don't know, a power bank or any sort of like battery, whatever thing I've set up to give it the adequate amount of voltage and current, that's fine, right? But let's say I wanna update this thing now. The circuit is built. The circuit is ready. Whatever you're plugging the robot into, it is assumed that this thing is going to be giving enough voltage and current to this device. But if I want to program the ESP32, I would then need to use, I would then need to plug this into, um, I would then need to plug this into, what do you call it? Sorry, I'm blanking here. I would then need to plug this into a computer, into a computer's USB port, unless I want to program it using a programmer, and then I would be, interfacing with various ESP32 pins. Then it's a different situation, right? Um, but like, if I want to be able to connect this to, if I want to be able to connect this to a computer, now there's a risk that the moment I connect this to the computer, all of these other things are going to start pulling current, and they're going to pull current from the USB port, which is then going to trigger an over current shutdown on the computer, just to save the USB port from destroying itself. So how am I supposed to go about doing this? The first thing that came to my mind there was maybe I need some sort of mechanism in place to detect whether there's a power bank connected to this, or if it's connected to a computer. And a lot of the different methods that I found, they don't seem to be completely foolproof. They don't seem to be completely safe from failure. Um, One idea that I had was I could try using a USB breakout board, and that breakout board would then be connected to all of the pluses and minuses, or VCCs and grounds that need to be connected. But because apparently the USB port on the ESP32 dev board, it tends to be connected directly to VIN on the ESP32. So like, if I'm using a USB breakout board, I would need to connect the plus to the ESP32's VIN. But according to Gemini, apparently the USB circuit, and therefore I think even the voltage regulator, I'm not sure, but the USB circuit, whatever the USB circuitry is there, it's directly connected to VIN. And so if I try to give power through VIN, if I'm actively giving power through VIN, but then I also connect the USB port, there might be like a weird situation going on there. I don't know what's going to be giving power to what. So to avoid that kind of situation, Gemini suggested putting in something called a Schottky diode, and that's going to prevent current going from the ESP32 back towards the breakout board. And so far, that's all I've gotten. That's how far I've gotten in terms of that research, because I got busy doing other research. As I was talking about this, I got this idea that, okay, fine, what if I'm not able to program this microcontroller from the computer directly anymore, or from the USB port directly anymore? There's nothing stopping me from using an actual programmer. So like, you have these I don't know exactly what they're called, but they're like USB flashing slash debugging utilities. I'll have to look into what the exact hardware is called. But these utilities, they allow allow you to both program and debug your microcontroller. So you usually they're usually chips that have USB connections, so you can connect them into your computer, and then you connect on the other end. You have a bunch of pins that you would connect jumpers into, and the other end of those jumpers would be connected to your ESP32's specific pins for programming and debugging purposes. I feel like that's going to be the best way to go about this programming situation. Yeah, because at a certain point, you know what? I should have a conversation with Gemini about this. But then I'm gonna have to describe the entire thing again. Um, though I have that conversation open, so I could just ask Gemini about that, or maybe I closed that conversation because I was done asking that question. I think I did close that conversation. I'll open it up again. That's fine. Um, okay. So, where was I in this conversation? I've kind of like branched out way too much. Okay. Right. Mathematical deadlock. Okay, so we are gonna explore the ticks thing. So since the hardware cannot make, actually, I was asking Gemini another question, right? Yes, yes. I was asking about like what controls this this speed and what controls the length of the tick. The length of the tick is controlled by the the clock speed, but then what is the clock speed controlled? Actually, no. Is it? Well, yeah, yeah, it is. It is. I was gonna be like, okay, why can't one tick be longer? But then our limitation there is that everything has to fit within a second, right? Frequency is measured in terms of cycles per second. So if one tick is one cycle and one tick is 12.5 nanoseconds in this case, so our total number of cycles, our total number of ticks is 80 million ticks per second. If we try to increase the length of one tick, that kind of increases the entirety of the frequency duration past 1 second. So it's not that frequency anymore. Okay, okay. Right. It sounds like you're digging into the heartbeat of the ESP32. You've hit the nail on the head. The frequency determines the tick length, and in the world of microcontrollers, everything starts with a tiny piece of vibrating quartz. Here's a breakdown of how that 12.5 nanoseconds tick is born. The source, the crystal oscillator, also called X-tal. That's interesting. Okay. The ultimate decider is a physical component on your ESP32 development board called the crystal oscillator. Most ESP32 modules use a 40 megahertz crystal. This crystal vibrates at a very stable fixed frequency when electricity is applied. However, 40 megahertz is in 80 megahertz. True. To get the speeds needed for the CPU and peripherals, the ESP32 uses a multiplier. The multiplier, that's the phase-locked loop. Since a 40 megahertz clock is a bit slow for a high-performance chip, the ESP32 has an internal component called a PLL. The PLL takes that stable 40 megahertz signal and clocks it up or multiplies it to a much higher frequency, typically 320 megahertz or 480 megahertz. The high speed internal clock is the raw material for everything else in the chip. Okay, the APB clock and the divider. Now we have a very fast internal clock. Hold on, we are talking about an internal clock now. Wait a minute, there's an additional layer here. Yeah, I think we are learning about an additional layer. Okay, now we have a very fast internal clock, but we don't always want our peripherals like PWM or I2C running at 320 megahertz. It would consume too much power and be difficult to manage. This is where dividers or prescalers come in. The hardware the hardware is configured by the bootloader or your no STD initialization code to divide the high-speed PLL clock down to a standard frequency. For the ESP32, the APB clock is typically hard-coded to 80 megahertz. The math that gives you your 12.5 nanoseconds is the inverse of the frequency. Right, okay, so now we have to factor in the frequency of the internal clock. Time for a new conversation. Hey, in the ESP32, I'm learning that PWM depends on an APB clock, but I'm now also discovering that APB clock depends on another clock. Is there another layer here that I'm not aware of? Well, the answer is yes, but I want Gemini to tell me exactly what it is. Okay, you've hit on the classic onion layering of microcontroller architecture. You're absolutely right. The APB clock isn't the top of isn't the top of the food chain. It's a derivative of the system's core timing resources or the core timing sources. In the ESP32, the clock tree is a bit of a hierarchy designed to balance high performance with power saving. Here's how the extra layer breaks down. The root sources. Before you get to the APB, the ESP32 looks at its hardware oscillators. The primary source is usually an external crystal oscillator, typically 40 megahertz. This is There are also internal RC oscillators, but they aren't stable enough for precise PWM. The PLL, this is the multiplier. Wait, that's crazy. Okay, hold on. This is interesting. So I thought it's only using a multiplier of 2, but apparently it's doing more than just 2. So this is a multiplier layer. Since a 40 megahertz crystal is too slow for a high performance CPU, the ESP32 uses a PLL. The PLL takes the extal frequency and pumps it up, usually to 480 megahertz. Okay, from this high frequency pool, the system derives the CPU clock and the PLL D2 clock, PLL divided by 2, then the APB clock layer. Now we get to your specific interest. The APB clock is typically derived from the CPU clock or the PLL. In a standard high performance mode, the APB clock is fixed at 80 megahertz. It acts as the bridge clock for most peripherals, including the LEDC PWM and the MCP WM controllers. The PWM divider, the final layer, even once the 80 megahertz APB clock reaches the PWM peripheral, there's one more layer, the clock divider. Okay, yeah, so we need to divide that up because 80 megahertz is way too high for PWM. Okay, that's fine. Why this matters in your project? The hidden layer can cause a headache when you use light sleep or dynamic frequency scaling. You know what? Okay, wait. Hold on. So where exactly is APB clock getting its um, clock signal from? And I'm assuming that gets scaled to, just like we have to scale to use APB clock in PWM? Exactly, you've spotted the gears within gears. To answer your first question, in most standard operating states, the APB clock gets its signal from CPU clock. However, the CPU itself is getting its signal from a high frequency source called the PLL. Think of the PLL as a frequency multiplier that turns a modest crystal vibration into a high speed engine. The scaling chain. Yes, your assumption is spot on. There is scaling at every single jump. It looks like a cascading waterfall of dividers. Okay, so the root is xtal. Holy shit, dude! I had no idea this was the case. I thought the crystal was generating 80 megahertz, and that was going directly into APB. Holy shit, dude! Okay, all right. Uh, the root xtal, a physical crystal, vibrates at 40 megahertz. Then we have the multiplier, which is a PLL. The internal PLL circuit multiplies that 40 megahertz up to a massive 480 megahertz. Then the CPU scale. The CPU divides the 480 megahertz usually by 2 or 3 to to run the CPU at 240 megahertz or 160 megahertz. This is making me wonder if we can overclock the ESP32 to run at a faster speed. Yeah, yeah. This is making me wonder if there's a way to overclock the ESP32. Of course, it's gonna get hot and consume more power, but I'm wondering if that's possible. Okay. Then we have the APB scale. The APB clock is then derived by dividing the CPU clock. By default, the ESP32 locks the APB at 80 megahertz, so a divide by 2 or divide by 3 depending on the CPU speed. The peripheral scale, finally, your PWM controller takes the 80 megahertz and uses its own prescaler to get down to the specific frequency you want for your motor or LED. Damn, now I'm hoping in the past I didn't accidentally say that the oscillator was directly feeding the signal um, into the APB clock. I'm trying to remember if I said that. If I did, shit, my bad. That was wrong. And apparently, this is how it works. You have an oscillator that generates 40 megahertz, a fixed 40 megahertz. Then you have a PLL that essentially upscales that to 480 megahertz. Then you have the CPU clock that downscales it to what was said, I think 280, 160, something like that, 240, 160. Yeah, 240 or 160. And then the APB clock reads the CPU clock and scales the frequency down to get that high frequency down to 80 megahertz. So that's how the APB clock is getting 80 megahertz. What I was assuming, and I think this is where I'd given out wrong information, that the oscillator is generating 40 megahertz, and then there's a circuit that's multiplying this 40 megahertz by 2, so it becomes 80, and that's how APB clock has 80 megahertz. I think yeah, I definitely got that bit of information wrong. Holy shit, dude, there's I need to dig into this stuff a lot more. Well, I guess that's what I'm doing here, right? I'm trying to understand how this works. The whole reason that now I know that this is the case is because I dug into this. My question was something completely different. My question was like regarding how, you know, oh shit, I just noticed the time. Okay. Okay. You know what? Okay, this has been fun. We streamed for a good 2 hours, and I do wish I would have started the stream earlier, but I got busy disassembling my my modular breadboards and creating what you're seeing right now. But yeah, that's going to be it for today's stream. We made a good bit of progress today, and we're probably going to continue doing this tomorrow as well. Um, I think so. We are probably going to continue doing this tomorrow as well. And yeah, let's see what we learn tomorrow regarding all of this very interesting clock speed stuff. I have a bunch of reading to do. I need to finish all of this reading so I can move on and close those tabs. But yeah, that's going to be it for today's stream. I hope you guys have a nice day, and I'll see you all next time. Peace.